Start. I hope we're going to be able to navigate the computer here. Let's see here. A little bit about myself. I'm Thomas Milner. I'm a professor of surgery and biomedical engineering at the Beckman Laser Institute and University of California, Irvine. And want to thank you all for coming out so early. We have a small group here, but that hopefully will be nice for questions. So let's see if I can get next.
All right. Thank you, Tom. Good morning to everyone. It's a real pleasure to be able to share the story of our journey in commercializing this product from its nexus as just an idea in academia to a medical device that's now in use globally. I have to start with some disclosures. So my lab receives support from Olympus, and then I have a financial conflict of interest as a co-founder of Planoptica and another company called Kubanda. So again, this story is going to be maybe in nice contrast to the next speaker you'll hear at the targeted towards very low resource settings for global health applications. And basically, we built this device to increase the throughput, the efficiency, and the ease of prescribing eyeglasses to places where it's needed most. And if we look at the one metric of health, life expectancy versus investment per person per year, you see a similar trend with any other metric, and that's diminishing returns. So the more money you're spending, the less impact you're having in improving healthcare across many different metrics. And as innovators in optics and medicine here, we should really not solely focus on these very high resource settings, because you can actually have a much bigger impact in low resource settings if you're able to provide the same amount of healthcare for incrementally lower costs. The benefits on this curve the slope is much higher as you look at these low resource settings. And if we look at some of the problems in these areas, uncorrected refractive errors is a surprisingly large one, projected to be in the top 10 leading burdens of disease in these global health settings. Refractive error is poor vision that can be corrected with a simple pair of prescription eyeglasses. Short-sightedness, far-sightedness, and all you need is a prescription lens to correct a distant point, to make a nice spot on your retina. And this is a really impactful healthcare intervention. So unfortunately, given it might be surprising given how simple and effective this intervention is, there's an enormous need for prescription eyeglasses. There's over 1 billion people worldwide who have uncorrected refractive errors. The New York Times had an article a few years ago, and they called it the biggest problem you've never heard of. So this is just a far-reaching disease that affects everyone's productivity, access to education, and quality of life. And the eyeglasses that you need to solve this problem are affordable. So you can buy a high-quality pair of prescription eyeglasses in many of these low-resource settings. There's infrastructure to produce and distribute these eyeglasses. And they're considered to be one of the most cost-effective of all healthcare technologies, and yet we still have 1 billion people without these eyeglasses. So one of the major bottlenecks, not the only bottleneck, but a major bottleneck, is that there's not enough eye care professionals to determine the pair of eyeglasses that you need. If you look in the US, we have 1 optometrist or ophthalmologist for every 6,000 people. In India, it's about 1 per 250,000. And so this is a picture of an organization that we collaborate with called Aravind Eye Hospital. They have an eye camp here and are providing eye care to a village in southern India here. And these are all paying customers. So these are people that want to buy a pair of prescription eyeglasses. And the difference today is that Aravind has brought optometrists to this village. So if we look at the technologies that optometrists, eye care providers use, many groups have tried to tackle the problem of making it easier to prescribe prescription lenses. And I've grouped them here as the ones that kind of have a technical plateau, the ones that have limited accuracy. They're still impactful in certain settings, but there's a technical limit to how accurate you can get with these groups of technologies on the left. And if we look at the ones that are in common use for the standard of care accuracy, none of them meet the 3 criteria that you'd really want simultaneously to be met to make an impact in low resource settings. We'd want something that's affordable, accurate, and easy to use. And there's nothing really that does all 3 of these, satisfies all 3 of these requirements simultaneously. So the project goal here, we essentially looked at the wavefront aberrometer here, which is very accurate, used to guide LASIK surgery, and thought about ways to make it much lower cost and easier to use. And that's something that not a lot of work had been done on before, because these have been designed for cost-insensitive applications. But with all the improvements that we've had in machine learning and the dramatic cost reductions and performance improvements we've had in camera and illumination technologies, it seemed like this might be possible to make a very accurate and easy to use, but very low cost wavefront aberrometer. So that was the goal of the project. Just to briefly give you an idea of how this works, we make a beacon on your retina by shining a pencil beam of laser light. We collect the remitted light with a Shack-Hartman lenslet array, and we look at how the spot pattern is distorted from the aberrations of your eye. So if you have poor vision, those spots are moved around on the sensor. The phase is encoded as a translation at the sensor plane by this lenslet array. So we started by building the conventional wavefront aberrometer with all the bells and whistles, and then we systematically removed components, substituted consumer-grade components for these high-end research or medical device components, while simultaneously building new algorithms to try to process these data and maintain or even improve the accuracy that you might get by analyzing Shack-Hartman spot diagrams. The end result was something we called the QuickSee. So we took out the Bedell relay system. There's no moving parts. We used consumer-grade components and made it very, very simple and compact. And so this will give you data like this. This is on the left, the data that you get from someone with good vision, and on the right is someone that's short-sighted. And you can just see by eye there's a dramatic difference in the shapes of these spot diagrams. So we did an initial pilot study with the New England College of Optometry, and we compared against gold standard. This is called the Ferrari of autorefractors by optometrists, so the best one you could get, and the gold standard of subjective refraction. And when we compare the accuracy of the eyeglasses prescribed versus the gold standard subjective refraction, the device that our first prototype that still had some electrical wires and duct tape hanging out of it, actually performed better than this very nice autorefractor. And the reason is that we record a video of the eye, and our algorithm will analyze hundreds of frames of prescriptions, and we can consider all of that information in our eyeglass prescription. And that's in contrast to the conventional way of autorefraction, where you try to align a system to get the very best image, and then you take a single snapshot. And so in essence, that's why we're able to improve the accuracy here. So this began the commercial translation of this project. We saw a lot of potential in the initial study that we conducted. And so instead of, this is an important lesson that we learned from this process, instead of immediately going to try to improve the technology further and fundraising, we went to the customer to try to understand more about their constraints and needs. So we visited Aravind Eye Hospital in southern India, and we took this crappy prototype with us and did a lot of measurements and got user feedback very early on, before we had raised funding, before we had finalized the prototype, to help to include them in the design process and the innovation process. So we did lots of voice of customer research. We did user-centered design, where we thought about the various use applications and use cases that this technology might have, the price points that we could work with, and form factors that might be conducive to very easy, intuitive use and high throughput applications where you want to refract hundreds of patients in a day. This can be done very cheaply, so you don't need to raise VC funding to do your user-centered design. We did this with very low resources in our organization, and this helped us down the line maintain our independence and really keep our goal of introducing a technology that would impact these low resource settings. So at the same time, we're doing voice of customer research and user design, user-centric design. We're also improving the technology and the algorithm. After several years of development, we had this standalone initial prototype that we can conduct a large clinical study with the target users collecting the data and not us as researchers that kind of know how to get it to work well. So the device records about a 10-second video from both eyes and has a touch screen on the side of it. It's self-contained with a 20-hour-ish battery life. And it works indoors, outdoors, and gives a prescription at the end of those 10 seconds. So we did a large clinical study in southern India. This is with, again, Aravind Eye Hospital. We tested 708 patients in both urban and rural settings. And we compared the eyeglasses that this QuickSee device prescribed to the highly trained, very experienced optometrist, their subjective refraction. And we compared the visual acuity that you get from the lenses from either source, and then asked the volunteer, the patient, which pair of eyeglasses they would prefer, and they didn't know where those glasses came from. They were just labeled A or B. So from this study, the visual acuity improved from about 0.3 logmar units to close to 0. The X is the mean value of the visual acuity from the QuickSee versus the optometrist. The optometrist did beat the average visual acuity compared to the autorefractor by about 0.02 logmar units. If you're not familiar with that, that's one letter on the logmar chart. So on average, patients looking through these eyeglasses got to within one letter of being able to read this chart compared to what you get from eyeglasses from the very experienced optometrist. Now, if we ask the patients which pair of eyeglasses they prefer, looking at all patients, they preferred the optometrist more often, 42% versus 33% from the device. This was all comers, so we had patients from 15 to 80 years old, cataracts, people that have never used computers, coming in for serious eye diseases into these clinics. If we look at the pre-presbiotic patients, the majority of the patients that were under 40 years old, there was no statistically significant difference between a preference of eyeglasses from the QuickSee versus eyeglasses from the optometrist. And this, we think, is due to them just being more comfortable with using these types of technologies. And this is our initial, not our initial, this is a very early prototype. And as you probably know, with machine learning models, they get better with more and more data. So the system we have now is much more accurate. So summarizing the results of this study, we could train a high school graduate in just a couple hours to use this device. And this same high school graduate recorded and measured prescriptions for these 700 plus patients. The device gave similar visual acuity and preference to the prescriptions given by an experienced optometrist. And if we look at the younger population, we saw an even better preference for the prescriptions from the QuickSee device. So we started a company to commercialize this now. This is what the product that we were selling for several years looks like. We actually introduced a new one about a year ago, but it's being used all over the world now. So this is really gratifying as the co-founder. There's large NGOs that are purchasing this for vision eye care missions. It's being used in hospitals, school screening settings, and by retailers. And we've surpassed about actually 5 million pairs of eyeglasses prescribed this year. And most of these are in low resource settings. So this is being used very heavily in southern India, southern Asia, India, Bangladesh, Africa, and South America. So some takeaways I'd like to end with before questions. I think it was one thing I really appreciate now going through this journey is that understanding the need and product market fit early, I think, was very beneficial to be efficient with our development resources. We tried to do several things in parallel, and I think as an engineer, my group often focused on the technology, but I think that would have hampered the development of this design. Another thing I think that's really exciting now, if you're in optics and lasers, is that the performance and cost of these technologies has changed so much in the last several decades. And so there's new opportunities, I think, for innovation here, for very impactful new medical devices. And then I encourage everyone to look at opportunities for impact in low resource settings. And with that, I'll thank you for your time. I want to acknowledge the co-founders of Planoptica, Daryl, Eduardo, and Shivang, and I'm happy to take any questions.
Thank you, Nick. That's great. Questions?
Can you replace a commercial grade auto router with this low cost?
Yes, yeah. So the company now, we kind of have a cross-subsidization model where we are, the company is sustainable and growing because of our sales in the US, Europe, Japan, Korea, and able to sell it for a very low cost in other settings. So we are selling quite a few to high resource settings as well now. It is a tough market. So if you look at the auto refractor market, the companies that are in this are generally losing money on their auto refractor units. They last for 30 years. People know how to use them and they become attached to them. Every optometrist in the US already has an auto refractor, so you're trying to sell them something new that's better than what they have, but they already have something. So it's a difficult market, I think, on its own. But for our social impact mission, we still have a value proposition there, and we're using that to cross-subsidize the development of the device for low resource settings.
Other questions? I guess I have a couple. One, has your product given rise to, you showed that curve, and you focused on the early part where the slope is great. Has it given rise to products that may be further to the right? I guess let me ask both questions because they're kind of coupled. So I'm struck by your last point of saying going into the low resource settings first just makes a lot of sense because it sort of drives curves the thing the right way, I would say. So could you comment on that sort of bigger picture of trying to do what you've done very successfully and then its subsequent impact sort of along that curve?
Yeah, thanks, Tom. That's a really interesting question. So we actually struggled a lot in the beginning because, as a startup company, we were in Boston. Kind of the VC model is to look for disruptive technologies and billion-dollar markets. So we got some pull to make a kiosk for Walgreens and CVS and kind of take the optometrist out of the loop for prescribing in high-resource settings. I think that still is a possibility, and there are some companies going after that at how you really change things in high-resource settings where there's still need for innovation here. And our argument was that we could leverage non-dilutive funding, philanthropic funding, the vast numbers, low development costs to introduce something in low resource settings to really prove out the technology, make it super robust, and then downstream make something better for high resource settings. That was kind of the vision that we were trying to raise funding for, and it wasn't that successful actually. It was hard to have that complication in the story for someone that's optimizing for a return on investment. We still have that goal, but there's so much to do in these low resource settings that it's been on the back burner, and honestly, I'm not sure if we're going to get there. So we are making impact in high resource settings is for Planoptica now has been in the low resource settings of the US. So rural areas, poor areas, inner cities, prisons, homeless camps, the places where portability and robustness and high throughput are important are benefiting from here, but we haven't, I think, to quickly answer your question, at the very high end, we're not making an impact right now. We still hope to, but there's so much to do for us right now in the middle and lower end.
Okay, thank you, Nick.
All right, thank you.